welcome to this video where we're going to have a look at tidal locking. Now, tidal locking can happen to planets and moons, so it's not just confined to one or the other. Now, if we have a look at planets, so this is a plot of the currently confirmed exoplanets, and we've got a wide range of planets on that plot. So you've got the radius plotted against the period. Now, if you have a very small orbital period, it's going to be quite close to its star. So I've noted here in the blue circle planets that are very close to their star. Some of those will be classified as ultra short period exoplanets as well. So if they're very close to the star, they can become tidally locked. Now, most major moons in our solar system are already tidally locked. So Enceladus, which is Saturn's moon, the moon, which is obviously ours, we should be aware that actually it always has the same face facing towards us. Europa, which is a moon of Jupiter, Triton of Neptune. Now, there's actually lots more than that are tidally locked, but that's just an example, really. So all of those major moons are tidally locked. So what is tidal locking? Well, it's where the rotation period of the smaller object is the same as its orbital period. So as it orbits around, so if we take the example as a planet orbiting its star, it takes so long to do one orbital period, but the time it takes to do one full rotation matches that. So the same face of the smaller object is always facing towards the star. So if you were looking from the star outwards, you'd always see the same face. For the moon, it's fairly obvious because we look at the moon, we only see one face. So on the right-hand side is what we always see of the moon because it's tidally locked. We never get to see the far side of the moon from Earth because its rotation period matches its orbital period. So it's always, we can never see that far side. So what's actually causing it? Well, it's due to strong tides because they're close to each other. The gravitational force and the tides that it causes deform the object. So as that object is spinning, there is like a tidal bulge, or the object is trying to be stretched as it spins. Now, as it does that, the material of the object is trying to resist that deformation. So depending on the material that's made of, the composition, it's going to resist that in a different way. But the end result is that resistance to the deformation causes a loss of rotational energy, which then gets dissipated as heat internally into the object. So the object actually increases in temperature whilst it's slowing down. So that tidal friction causes it to heat. Now, a good example of that is one of Jupiter's moons. So Io here has actually got volcanoes erupting from it, which have been imaged. And that tidal friction can also be responsible for volcanic activity on these objects. So there's a few moons actually that have volcanic activity, and they're mostly driven by this tidal friction being close to their planets. Now, the tidal locking can also occur with a larger object. So the example I'll give here is Earth and Moon. The Moon is already tidally locked, so it always has the same face facing towards the Earth. But the Earth is actually still slowing down in rotation. So our days are going to get longer, and at some point we may have the same face always facing towards the Moon. So we'll both be tidally locked to each other. Now, Pluto and Charon are smaller than the Earth-Moon system, but they are already tidally locked. So they both have the same face facing towards each other all the time. So they are both tidally locked instead of just the smaller moon being locked to the larger object. So thank you for watching, and if you enjoy, you can check out some of the other videos.